Hello everyone, how are you? Welcome back to my channel. In our previous video, we have understood how to derive the change percentage in resistance when the length is changed by a small amount, or area of cross section is changed by a small amount, or the radius of the conductor is changed by a small amount. Now we will observe how the resistance percentage changes when the wire is stretched. Okay, so here we'll consider the same thing for all the questions. Means all means the same thing. When the wire is stretched, when the wire is stretched or drawn or twisted or elongated. Okay, elongated. So when the wire is stretched or elongated or drawn or twisted, we there is a change in the dimensions of the wire such that the volume of the wire or the volume of the conductor should remain constant. Okay. Now let me write first the formula for resistance of a conductor in terms of resistivity, length and area of cross section. So R is equal to rho L by A. Okay. Now, so what I am trying to do is I want to know what is the percentage change in resistance for small changes in length if the wire is stretched. If the wire is stretched, the length will increase. Okay. If the length increases, the area of cross section should decrease so as to maintain the volume as constant. Therefore, first I am deriving the percentage change in resistance for change in length. Okay. So this is the case of stretched, drawn or twisted or elongated. Okay. So for small changes in length, for small changes in length. In order to know that, first we need to multiply the expression or the equation, the LHS of the equation with L and divide with L on both sides. So that I will get R is equal to rho L square by A into L. Now it will give us rho L square by V. Now when the wire is stretched or twisted, the volume remains constant. Rho is already a constant which depends upon type of material and the temperature. Hence, if I apply log on both sides, applying log on both sides, we can obtain log R is equal to log rho plus log L square. So you can write this as 2 log L, right, minus log V. So when you apply the log on both sides and apply the properties of logarithms, you will get this equation. Okay. Now I am only concentrating on changes in length. That's why the volume remains constant. So it is 0 if you take the differentiation. And for log rho, if you take differentiation, it will also become 0. Hence, when you differentiate on both sides, you will get 1 by R into delta R is equal to 2 into log L differentiation is 1 by L into delta L. Okay. So delta R by R which is the fractional percentage or percentage of change in resistance, it is equal to 2 times delta L by L. This is the case when wire is twisted or drawn or stretched, because in that particular case the area and the length are adjusted in such a way that to maintain volume constant. Okay, next we will observe what happens to the change in resistance when the area of cross section, for small changes in area of cross section. Okay, for that, first I want to write the expression for R. Let me write it. So R is equal to rho L by A. Now what I need to do, I need to multiply with A and divide with A on both sides, so that I will get R is equal to rho L A by A square, and L into A is volume, so I can have rho V by A square. Okay, now what I am doing, I need to apply log on both sides, so that the equation will be log R is equal to log rho plus log V minus A square. Log A square becomes 2 log A. For small changes in area, here we are doing for small changes in area, that we need to keep in our mind. Okay, for small changes in area, if you differentiate on both sides, you will get 1 by R into delta R, and the differentiation of log rho is 0. Differentiation of log V is also 0 because they are constants. And for minus 2 log A, you will get minus 2 into delta A by A. Okay, so finally it can be written as delta R by R is equal to minus 2 times delta A by A. This is the relation between small change in area creates a small change in resistance, and to find the percentage of change in resistance, we can use this formula. 5 minutes. 5 minutes. Okay. Now let me move to the last case study, which is for small changes in radius. Okay, in order to know that, first I want to write the previous equation. Okay, so let me do that with a separate color. Okay, now R is equal to rho L by A. Now what I did, I just multiplied with A on both sides, numerator and denominator. So rho L A by A square. Now it can be written as R is equal to rho V by A square. And uh, we know that A is nothing but area of cross section, which can be written as pi r square, considering the circular cross section. Hence R is equal to rho V by A square, means I can write this as pi r square whole power 4. Now what we'll get? It is rho V by pi square into r power 4. Applying log on both sides, you will have log r is equal to log rho plus log v minus, I can write log pi square as minus 2 log pi, and as r power 4 is also in the denominator, I can write minus log r power 4 can be written as 4 log r. Okay, now differentiating on both sides, you will have delta r by r, which is equal to differentiation of log rho is 0, differentiation of log v is also 0, differentiation of 2 log pi, it is a constant and it is also equal to 0. Therefore you will have minus 4 log r. For log r, the differentiation is 1 by r into delta r. This is for small change in radius, for small change in radius of the conductor when the wire is stretched or drawn, or when it is twisted. Therefore delta r by r is equal to minus 4 into delta small r by r. This is the relation between percentage change in resistance for a small change in radius of the conductor. So in this video, what we have what we did is we found the change in resistance or percentage change in resistance for a small change in length. Similarly, percentage change in resistance for small change in area of cross section, and then percentage change in resistance for small change in radius. And these three formulae are applicable only in a situation when the wire is stretched, when the wire is stretched or drawn or twisted. In this situation only we can use these formulae. Otherwise, in normal situation we can use the formula which we derived in our previous video. You can observe here. So you can use these three formulae in normal situation. Okay, I hope this video gives you some very important information about finding the change in resistance for a small change in length, area and radius for two particular conditions. One condition is a normal condition, means we are not changing, we are not disturbing the conductor, and another situation is we are twisting the conductor or we are stretching the conductor. Okay, so if you really like this video, please hit a like button and subscribe to my channel. Thank you very much.